In this video, we are going to finish the 3 graphs on the model building lab in our bonding unit. So I have the scales done for you for some of them, and I'm going to give you less and less of a scale as we go, but some of the scales I wanted to mention. So what you're going to be graphing is you're going to be graphing molecular mass, which is this column right here, and you're going to be graphing boiling point, which is this column right here. And so for the boiling point, it's a little bit difficult because some of the numbers are negative and then some of them are positive. So what you have to do is you have to start with the lowest number being the most negative. So here I started at negative 85 and I went up by tens. And then notice I got to, since I started at negative 85, I got to 5. I noted the 0 just to show you where it was, and then the next box would be positive 5 because that's 10 above negative 5, and then it goes by tens normally. And then you're going to plot molecular mass. So the way you do molecular mass is actually pretty simple. I'm gonna do one of them with each. So for these, I gave them to you. All it is the mass of the molecule if you add up the weight of the atoms. So we round them to a whole number. So F weighs, or H weighs 1, and F weighs 19. When I add the two together, I get the mass of HF, which is 20. And so that's how you do it. So it's going to be 1H plus 1Cl rounded, 1H plus 1Br rounded, 1H plus 1I rounded. This is what you end up getting. And now you're going to plot the points. So when you plot these, it's pretty simple. For this one, we're going to go mass 20, boiling point 20, put a dot, label it. So for 20, it's going to be in the middle. It's going to be right here, and I'm going to label it HF. And then the next one is going to be HCl, which is going to be negative 85 and 36. So 36 puts it around here, and this is going to be HCl. For the next one, it's going to be negative 66 and 81. So negative 66 and 81 puts us like right there, and that is HBr. And then the last one, HI, 128 and minus 34. So minus 34 and 128 will put us around here. And so here's the pattern, or the lack thereof, right? If you graph it, it's going to look like this. You're going to use a ruler. Okay. And what you would expect to happen is you would expect the boiling point of HF to be somewhere in this range. If you look at this trend, you would say, okay, lower mass equals lower boiling point, lower mass, lower boiling point, and you would expect the HF boiling point to be somewhere in this area because lower mass, lower boiling point, yet it's very, very high. And then the question is, what's different about it? That's question 1. And so the key that you have to look at is you have to look at the intermolecular forces. It's going to have a different intermolecular force than the rest of them, and then that intermolecular force has an effect on the boiling point, which you should already know. As far as the title, you could just go whatever you're graphing on your X versus whatever you're graphing on your Y makes for an easy title for pretty much every graph ever. And so that is the first one. For the second graph, I'm going to do a lot less for you. So the molecular masses, I'm just doing the first one, for CH4 is going to be 1C, which weighs 12 when rounded, and 4 H's, which is 4 when we round them, obviously. And you add those together and you get the molecular mass of CH4. So that's all you do for molecular mass. You're going to do the rest. I'm not going to plot these for you either. And then for the scaling on the Y, the boiling point, again, it's negative 161 is the lowest and negative 52 is the highest. So what I did was I started at negative 60 and I went up by tens and I was able to make it work. For your title, it's going to be molecular mass versus boiling point. It's the same title for all of them. But what you're going to have to do is you're going to figure out the molecular masses, do the graph, and then for this particular graph, notice I say the question is, what's causing the gradual predictable boiling point increase? So for this one, as the molecular mass goes up, the boiling point goes up, and there's no weird exception on any of them. There's nothing different about them. They all have the same intermolecular force, so that's going to make things easy. And then for the last one, same idea. You're going to be graphing molecular mass, which you're going to calculate. I'm doing the first one for you, and you're going to graph it against boiling point. And that's what you end up getting. Now, for this, what you're going to do is for H2O, it's 2 H's, that weighs 2, 1 oxygen, rounded weighs 16, add them together, H2O weighs 18. That's all you do for the rest. And so again, the same trend. As the molecular mass goes up, the boiling point is going to increase, except there's one problem. H2O is an exception. So what they're going to ask is what's different about H2O? Well, turns out it's the same thing that was different about HF, and I'll let you figure that on your own. But you're going to see a very similar graph. You're going to see the heaviest molecule should have the highest boiling point, and then as you get lighter, it'll go down, and then as you get lighter, it'll go down, and then it should go down more when you get to H2O because it's the lightest molecule, but it shoots up like really quick, and then I want you to explain why H2O has a unexpectedly high boiling point for its size. And that should, if you need help on this, go rewatch my intermolecular force video, and that should explain pretty much all of it.